Welcome to yet another session of Introduction to Photonics. So, yesterday we started discussion on semiconductor light sources and detectors. So, we understood that carrier transport which is specifically important from the perspective of light emission and detection is different for semiconductors compared to what we have so far discussed in terms of dilute atomic systems. So, we realized that there is something called a conduction band and a valence band, and we got to the point where we realized that you could have carriers being transported from jumping from the valence band to the conduction band. That's in the case of an electron jumping from the valence band to the conduction band. That would constitute a light absorption. So, if you have a light with energy greater than the band gap energy, then that could get absorbed, leading to electron hole pair generation, which we will come back and discuss a little more detail when we get into semiconductor light detectors. But for today we will focus on light emission, and light emission essentially happens when you have an electron recombining with a hole. So, electron in the conduction band recombining with a hole in the valence band could lead to light emission, especially if the band gap is much greater than the thermal energy. So, typically we are looking at band gap energies. For example, I did not mention this yesterday, for when we talk about Eg, the band gap energy for silicon, it is about 1.11 eV, whereas Eg, the band gap energy for gallium arsenide, is about 1.42 eV, right. So, you have essentially light emission when this recombination event happens, and you could possibly look at light emission also being stimulated. So, if you come in with a photon with energy greater than the band gap energy, and at those corresponding energy levels you have an electron and a hole, then you can actually have stimulated emission. Okay. For example, I should emphasize the fact that there should be an electron and a hole present at those energy levels. For example, if you come in with h nu like this, and that energy corresponds to let us say something like this, and if you do not have an electron and hole present, an electron present in the conduction band and a hole present in the valence band in this corresponding energy levels, you will not have stimulated emission, you will not have gain. You understand that? So, the presence of an electron in the conduction band and a presence of a hole in the valence band with and the energy level difference, if it corresponds to this h nu, then only you have stimulated emission. Okay. So, let us now move forward and start looking at semiconductor light sources in a little more detail, and we will start with talking about. So, what we will attempt to do today is to understand light emission in a semiconductor light emitting diode. Okay. So, what do we need for that? Well, so far we have been looking only at p-type semiconductors and n-type semiconductors. So now it's time to look at p-n junctions. Okay, what if you bring a p-type semiconductor and an n-type semiconductor together? Okay, so let's say you have the p-type on this side and the n-type on this side. Okay. Now we know that the p-type, the majority carriers are holes, and the n-type, the majority carriers are electrons. So the moment you bring them together, you are going to have electrons leaving from the n-type semiconductor, and that leaves behind some fixed charges, okay, with positively charged ions. And similarly, when the holes leave from the p side to the n side, that is going to leave behind this fixed negative charges. Okay. And since these are fixed charges, and of course you can say if these are positive and this is negative, then there is a small electric field that gets developed over there, and since these are fixed charges, they are depleted of any mobile charges. This region is called the depletion region. Okay. So you have a depletion region where you do not have any mobile carriers. Okay. And of course you can also say that there is a electric field across that, and correspondingly there is a potential difference that is developed across that junction. Okay. So let us look at this in a little more detail. Let us look at it from the perspective of the energy level diagram. One of the things that happens is these charges will move across until two things happen. One is that the Fermi energy on either side is going to become equal. Okay. So that Fermi energy is going to be uniform across the structure. And the other is, of course, you have a potential barrier there, and which discourages further diffusion of carriers across the junction. Okay. So those are the two things that happen. So let us look at this in a little more detail. First of all, if we say on the n side, if the Fermi energy is over here, we know that the conduction band cannot be very far from that point. So the conduction band on the n side is going to be like this, and then you can say the valence band is somewhere over here, right. And similarly, you would say that if your Fermi energy is like this, on the p side the valence band has to be close to that Fermi energy, and the conduction band is somewhere over there. So what you have here is a barrier that is created. This barrier here can be represented as the electronic charge multiplied by certain voltage V naught. Okay. So of course you can also look at the distribution of the electric field across this junction, and to do that you, let us say you are tracking the charge density. Okay. So the charge density is negative charge density on this side, and then that is going up to positive charge density on the other side, right. So, this is in terms of charge density, right, and just to make sure this is in terms of energy over here, right. And we know from Gauss's law. So, Gauss law tells us that whenever you have these fixed charges, you have a divergence of the electric field, or basically you can just say del dot D equals to rho B, right. The electric field, divergence of the electric field displacement is given by the volume charge density, and of course, the integral form of that will say that integral of d dot dl is going to give you, is going to be equal to the charges present. So, correspondingly, if you look at the electric field across this region, so you have an electric field that goes like this. So, this is in terms of the electric field, and this electric field, this which corresponds to this built-in potential, it acts like a gate. So, it basically says, okay, I cannot allow any more diffusion of charges on either side, beyond a certain point. And that equilibrium condition is typically achieved when the Fermi energy on both sides are equal or uniform, right. So, any questions about this so far? Okay. So, that is a regular PN junction. Now, interesting things happen when you connect a voltage source external to this structure, right. When you apply a bias, let us say first we consider a positive bias, let us call this VB, right. So, when you apply that positive bias, it essentially means that you are injecting carriers. So, you are injecting carriers, you are injecting electrons from this side, and you are injecting holes from this side. Okay. So, what that ends up doing is it ends up actually also reducing that potential barrier. So, it will start moving the Fermi energy on either side apart, such that the barrier is reduced. Okay. And of course, when the barrier height becomes 0, that means there is a free flow of electrons from left to right, and holes from right to left, electrons from right to left, and holes from left to right. Okay. So, essentially we say that and of course, you can look at the converse also. You can say that if my bias is negative, which means that you have reverse bias, then the barrier height becomes so much more that you do not have any possibility of the charges coming across, going across the junction. The electric field potential at that junction is further enhanced. So, it does not allow movement of charges. So, you would say that under reverse bias condition your diode does not conduct, and under forward bias conditions, especially when you have a bias that nullifies the built-in potential, then you have a free flow of charges across this. So, that actually brings us to what do we expect when what is the current we get to see as a function of this bias voltage, right. And what we will see in this case is under forward bias conditions, beyond a certain built-in potential, you have an exponential increase in the current, and on the reverse bias you should not see much current flow, but nevertheless there will be a very small current which may be called as IS, okay, just capital IS, right. And of course, you keep increasing that reverse potential, then these two layers keep going further and further apart. I mean the conduction band on either side is going further and further apart, that you may start seeing tunneling phenomena happen. So, beyond a certain point you will have a breakdown of your junction, and so beyond that it is not usable, right. So, breakdown happens. But when you consider this normal operating range, you can actually say that when you are tracking that current as a function of voltage, you can say that this is going to be given by Is exponential of E times Vb over kBt minus Is, and of course that should be such that that expression should be such that at Vb equal to 0, I equal to 0, right. So, that is what we have here, and when we have a very large reverse bias, very large negative voltage Vb, then the first term essentially goes to 0, and then all you have is the reverse current Is. Okay. So, what we will see is for all our emission, you need to have these carriers come across the junction, and so that they have a possibility of the recombining. So, the electrons are recombining with the holes, right. So, in this region we will have all your sources operating, and we will see that all our detectors are operating in typically in this region. So, forward bias of a PN junction, if your band gap energy is much greater than the thermal energy, then that forward bias can potentially give you light emission, and a reverse bias may be useful for light detection. Okay. Some of those specifics we will look into that shortly. Any questions so far? Okay. So, let us look at light emission. So, it so happens that when you talk about light emission, so when you are talking about recombination of electrons and holes effectively under certain forward bias conditions, your conduction band and valence band are aligned, and so you have all these electrons that are going from here and all these holes that are injected from here, and then you could have recombination, and you could have recombination events happening over here, which results in light emission. Okay. But in this picture, the problem is that recombination can happen anywhere. There is no confinement of these carriers, and once the recombination happens, the light can be essentially emitted anywhere. So, there is no confinement of the light also. So, to improve this, to essentially have some sort of confinement of the carriers as well as the light, you actually go through what is called an heterostructure. So, most of the practical light sources that you see actually involve one more layer, okay, which is typically known as the active layer. So, what do I mean by this? Now, an heterostructure is when you have the P and N, but you also introduce one more layer in between. Okay. So, what is different about this layer? Now, this layer is going to have a different band gap energy, right. So, we say the band gap energy of the P of this region and this region is equal, right. They have equal, so we can call this Eg1, right. So, on either side there is Eg1, and of course, so the P type, you say that the Fermi energy is going to be somewhere over here, and with the N type the Fermi energy is somewhere over here. But in this other material, suppose you have a band gap Eg2, right. Suppose you have a lower band gap, and of course, it is a P type. So, the Fermi energy is got to be somewhere over here, right. If you have that, then what happens? Now, of course, you say, how am I able to practically realize this? Is it like you take a material, let us say silicon, you dope it with phosphorus to get an N type, you take silicon, another block of silicon, you dope it with aluminum, you get a P type, and you take those two blocks and get them together. No, that's not how it works, right. So, usually what they do is there is something called an epitaxial deposition that happens. Okay. In this epitaxial deposition, what you do is you take a substrate, right, you take one substrate which is typically a highly conducting material, and then you deposit silicon on that, okay. And even as you are depositing silicon on that, you also allow phosphorus to come in to get deposited also. So, you are making the N type, okay, and then above that you are depositing. So, up to you achieve a certain thickness which is typically in the order of few hundred nanometers or maybe even a micron, and once you achieve that thickness, then you stop that deposition, Now you continue depositing silicon, but now instead of phosphorus you bring in aluminum. So you deposit that p-type layer on top of this. That is what we call as epitaxial deposition. Now to do this heterostructure, what you are doing is, now let us say you started with indium gallium arsenide phosphide, okay, that's a quaternary semiconductor. You deposit the gallium and arsenic, the proportion of that, if you change the proportion of that, the band gap energy changes. Okay. So you initially start depositing indium gallium arsenide phosphide to make that n-type layer, and then you change that gallium and arsenic concentrations, then you are actually, and of course the corresponding dopants also, and then you get a p-type layer, but with a different band gap energy. Okay, the proportions we are not going into the details, but that's just the idea, right. So you get a different band gap energy, and then on top of that you have another p-type layer with the original composition itself, right. So the band gap energy is the same. So this is what you do. So you have n-type, you have a thin p-type, and then on top of that you have another p-type, right. So what we are saying is these two layers here have one composition which gives you Eg1, whereas this layer has another composition which gives you a lower band gap energy. Okay. So, but your overall structure is going to be like this. This is just basically all these layers are sandwiched between two metallic contacts. So you put you deposit a contact over here, and this substrate itself, you may have a contact over here, and then you have a possibility of connecting that to an external bias source, and you have your light emitting structure or your detector also, depending on what sort of bias you put. Now what is the consequence of having a double heterostructure like this? One thing we can say is, once you put them together like this, the Fermi energy once again is going to be equal across this, and then what you see over here is there is going to be a step corresponding to the lower band gap energy, and then there may be a step over here corresponding to that n-type, and similarly on this side you are going to have, this is a p-type, you may have a small disturbance here, and then you are going to have a large step over here. So you have something like this. Okay. If you were to be perfect about this or more rigorous about this, I would actually see how much of a step I have taken here. There will be a corresponding step over here, right, and then there will be some bump over here, and similarly here also there will be a bump, but for all practical purposes that does not serve much much function. So we may just take it like this. Now what we are doing here is, once again we are injecting electrons from this side, holes from this side, right. So they travel up to this point, and then what they see is this barrier. So they cannot travel any further. So there is like a wall over there. So they get injected, they go up to a certain point, and beyond which they cannot go anywhere else. and the only possibility in that region where there is a huge density of these electrons and holes, there is a huge probability of recombination happening in that region. You understand that? So, it gets everything gets accumulated essentially in this p-type region, right, and at that p-type region it has nothing else to do but to recombine between themselves. The probability of recombination increases quite a bit in this sort of structure. So, then in this region you have all this recombination happening, and because of that you have light emission. Okay. An added advantage of this structure is that when you look at the refractive index across the structure, what you find is that typically when you have lower band gap, the refractive index of that region is actually higher compared to the other material. Okay, so this is in terms of refractive index. Okay, and what does that tell you? If you have higher refractive index, it starts behaving like a waveguide, right? It starts confining light in that structure. Okay, so this heterostructure provides both carrier confinement as well as light confinement. Okay. So, this we will see, so this is happening in this region which we are calling as the active layer. So, you have light emitted within that layer and also guided within that layer. Now, that brings up another point. If light is guided over that layer, there is also a possibility of some other event happening. What is that? You have carrier confinement as well as light confinement. So, you have the possibility of stimulated emission happening, because you have this carrier density, the electrons in the conduction band and holes in the valence band, and you have photons that are also guided in that region. So, you have a possibility of stimulated emission happens, and that is exactly the principle that we will use in lasers, where on either ends of the structure. So, on these ends, if you put a mirror on either facets, if you put a mirror, then you could have stimulated emission happening, and it could actually build towards a laser. So, in some ways it is easier to get a laser out of a semiconductor structure like this, heterostructure like this, than get LEDs. So, this is quite counterintuitive. You say for a laser you need to do this extra thing and all that, putting the mirrors and aligning and all of that. No alignment necessary. You are basically just cleaving the material, right? You do this on a large wafer. These days you can do it on an 8-inch wafer or maybe even a 12-inch wafer. You do it on a large wafer, you build it epitaxially, which actually takes a lot of time, because you are talking about laying one atomic layer on top of another, right? It is a very slow growth. But then you have done all of this, you look at this, each of these devices that you need is only like 100 microns in size. Okay, so you can dice it up into that many pieces. So, with one of these you can get thousands of devices literally. right? One processing like this, you can get thousands of devices, and that's the beauty of doing this semiconductor processing. You don't have to do one cavity after another cavity. You get thousands of these together, and when you dice it, right, you are essentially making a flat cleave on both sides, both ends of this material, and the refractive index of the material, if you talk about gallium arsenide, it's about 3.4. So, it is 3.4 in the material and 1 outside, air outside. So, what do you think the reflectivity is going to be? It's fairly high because the huge contrast between the material and things. So, it naturally has about 30% reflectivity on either ends. So, that 30% reflectivity can essentially bounce off more photons within that active region, and you can easily make a laser out of this. So, if you are trying to make an LED, your biggest problem is as you increase the current, it starts lasing, okay? And there is a big difference. I mean, when you are making an LED, you want light to be spread out. If you make a laser, light is going just in very specific direction, so you cannot use that for lighting purposes. So, what you have to do is to take care of that reflection as an extra step, okay. So, you may have to put some anti-reflection coating at the ends, or you may have to frustrate that reflection by making that surface rough. Okay, that seems counterintuitive. You are talking about an optical surface and you want to make it rough, because rough is essentially saying that light will scatter everywhere from that surface. But that is absolutely okay, because most of the LED applications require light to be scattered over a wide region, more the better, right. So, normally when the light comes out, it comes out only over some 30-degree angle or something. Now, if you put some, if you roughen the surface, it scatters light over a larger, range of angles, and that is actually better for lighting purposes, because it means it covers a larger region. Even in that case, people complain about light, LED light being very focused and it is covering only this region, whereas you used to have your fluorescent lamps which is covering a much larger region, and so on. So, you are having to put some extra diffusers beyond that. I think there was a question somewhere back there, yeah. Yes. That's true. That's absolutely true. That's a very good point. The question is that the middle region, which we are calling as the active region, is actually having a different band gap, which means that the emission is going one step beyond where we are right now, but we will talk about this in a few minutes. So, the emission is going to happen at a different wavelength compared to what happens if your recombination happens on either sides, and that is absolutely true. And so, you start with that requirement. You say I want to emit around 1.5 microns, you find a band gap which that is your central active region, which corresponds to 1.5 microns, and you alter the doping that on either side the band gap energy is larger. So, that is the way you go about designing these structures. Your target is your active layer, right, but you want on either side a material with larger band gap, so that we can achieve this carrier confinement as well as light confinement. Okay, understand that? Okay, so enough about structures and all that. So, let us go ahead and try to now put some current through this and see what happens. So, what we are essentially talking about is, let us say you can ground this, and you can apply some bias to the structure. What happens in that case? What happens is clearly, you have carriers injected into the structure, and when carriers are injected into the structure, they are going to go accumulate in that active layer, and then they are going to start recombining, and then you have light emission. So, let us actually track this light emission as a function of the injected current. Okay, so what are the so we are now talking about light emitting diodes. So, what are the characteristics of light emitting diodes? So, the first thing that we want to track is output power. Let us call this P out. How that output power changes, how P out changes as a function of current that is injected into the structure. Now, the rate at which you are injecting current will be I over the charge Q. You could have put E also, it does not matter. I mean, so yeah, we have been putting E as the electronic charge, so that we can remain consistent with respect to that. So, I over E represents the rate at which current is injected into this region. Now, so that talks about the rate at which carriers are injected into the structure, and these carriers would have to recombine and give you light with energy h nu, right, multiplied by eta int. So, what does this eta int signify? Not every electron hole pair is going to give you a photon, right. Somebody was asking yesterday what are the chances of non-radiative recombination. Chances are low from the perspective of recombination of electron with a hole and not emitting a photon, that thing is low, but nevertheless you could have these electrons colliding with each other, right, because the carrier density is very high in this region. So, the electrons could collide with each other and they might generally generate heat, and since they are losing energy as heat, you may actually lose that corresponding electron energy in the conduction band, and so that would be a non-radiative mechanism, because now you are not extracting a photon out of that those electrons. So, eta int can be defined as the total radiative emission rate over the overall rate at which the carriers are lost. So, that could be non-radiative mechanisms also. Okay. So, R rad over the total rate at which carriers are lost, represents this eta int. And since the rate is inversely proportional to the time, right. So, you can write it R rad as 1 over tau rad, tau r, let us call it, and similarly the denominator it's 1 over tau r, and this is 1 over tau n r. So, if you put that together, you get this expression that this is going to be equal to tau n r over tau r plus tau nr, right. We are just substituting r by 1 over tau. So, if you do that, then you get this expression. So, it basically says that if tau r is far less than tau nr, right, then eta int is going to be equal to 1, right. So, that is one of the advantages of this heterostructure, because what it essentially means is that you have these carrier accumulation which immediately says, okay, once the carriers are accumulated, they can immediately recombine. So, the tau r can be much less than tau nr in this case. So, for this heterostructures, you typically see that the values are relatively high, and so this could be 80 to 90% or 0.8 to 0.9 as far as this in gallium arsenide is concerned. In silicon, the story is different. In silicon, we understand that it is actually indirect band gap semiconductor. So, there is no like direct recombination that's happening. So, that recombination would have to be associated with typically a phonon or a vibrational mode that takes out that extra change in k, the momentum, and that means your eta int is much lower. Okay, the probability of radiative emission is much lower compared to the non-radiative emission in that case, and because of that, silicon material by itself, silicon diodes, PN junction diodes, do not give you very good light emission. Okay, so silicon, what is your band gap energy correspond to? We said about 1.1 eV. 1.1 eV would say that the cutoff is around roughly around 1.1 electron or 1.1 micron. So, the emission would be lower wavelengths than that, okay, and so you could potentially get visible emission from silicon, but the efficiency of that is very low because it is an indirect band gap semiconductor, which results in this eta int being very small. So, if you use gallium arsenide, or if you want to get, you do have these LEDs, right, these visible LEDs, that is how we are getting this visible light. So, you would ask what about these things, because gallium arsenide is typically used for longer wavelength emission, okay. But for these things you use a material called gallium nitride. In fact, a few years ago the Nobel Prize was given to the person that invented this gallium nitride material for light emission, okay. So these are typically gallium nitride based LEDs, which is actually once again a direct band gap semiconductor, and because of which the radiative efficiencies are much higher, okay. So that is one part, and this constitutes the total power that's generated within that structure, within that heterostructure, okay. But not all that power escapes the that structure. Why? Because if you look at what happens at this interface, right, this is the interface between let us say this is gallium arsenide and this is air, okay. Gallium arsenide has 3.4 refractive index, air has 1 refractive index. So, when light is incident on this, there is going to be reflection, right. Not all of that is going to go through, there is going to be reflection at that point. That reflection, that reflectivity is going to be given by n minus 1 divided by n plus 1 the whole square, right. That is going to be the reflectivity. Like I said, if you put n equal to 3.4 and you compute this, that will probably come out to be about 30%. So, this implies that the amount of the fraction of light that is transmitted is given by 1 minus n minus 1 over n plus 1 the whole square, which approximately be equal to no, it's not approximate, it's equal to 4n over n plus 1 the whole square. Okay. So, that is the fraction of light that is transmitted. Not only that, we say, okay, if you have some off axis sort of emission, that will also refract and go out like this. But you keep looking at larger and larger off axis angles, and especially at off axis angles greater than the critical angle, then what happens? If you have such a ray that is greater than the critical angle, it will be totally internally reflected, right. It will not escape that, that material. So, it will be totally internally reflected within that material itself, and you will not see the light come out of that. Now, if you look at the fraction of light escaping, that would correspond to 1 minus cos of theta c. Okay. So, that will be the fraction of light that is escaping, and this is cos theta c can be written as root of 1 minus sin square theta c, and sin theta c is nothing but 1 over n, right. So, this is root of 1 minus root of 1 minus 1 over n the whole square, okay, which if you do the math, you will find that it is approximately equal to 1 over 2 times n square. Okay. So, you have a certain reflectivity, and the other part is the total internal condition allows you to only send out a fraction of the light that is emitted. So, if you put both of them together, you get this other factor eta out, where eta out is given by 4n over n plus 1 the whole square multiplied by 1 over 2n square, and that is equal to 2 over n and n cancel. So, n multiplied by n plus 1 the whole square. Okay. So, only a fraction of the light that is emitted is actually coming out of that structure, okay. And that fraction, if you substitute n equal to 3.4, that is 2 over 3.4 multiplied by 4.4 square. So, that could be a very small percentage, it is just a few percent, right. So, it is only a few percent of the light that comes out of this thing normally. So, that is where we are saying that we will have to put some do something at the interface to frustrate the reflection. You can frustrate the reflection, you cannot do a whole lot about this total internal reflection condition. Of course, you can say that I am going to make this corrugated, so that total internal reflection condition also maybe you can frustrate that, right, and then you can have more light emission. So, those are some of the things that are done for these practical light sources. But overall, when you look at this entire thing, you will say that your output power is going to be increasing linearly as a function of as you increase your current, and that's what you're doing in the lab session this week. And up to a certain point, beyond a certain point, you will see some saturation and maybe even the power going down. This is a process that's called droop, okay, and that is the process that limits eventually the amount of light that you can get from a LED. These days people talk about going up to 8 watts, 10 watts LEDs are available, but these are typically multiple LED elements. Each LED element maybe only less than a watt, and that's because as you go to very high carrier densities in the recombination region, the active region, they end up colliding with each other, and so they generate lot of heat rather than light. Okay, so your non-radiative this thing is more possible than the radiative even beyond that point. So, because of that non-radiative processes dominating there, you will start seeing actually the power is dropping beyond that point, and it might end up melting the junction also at that particular point if the heat is not taken out properly. Okay. So, let me stop at this point. Where we are going with this is beyond this we will look at the modulation characteristics of these light emitting diodes and also the spectral characteristics of these light emitting diodes. So, we will do that before we jump on to laser diodes next week. Okay. Thank you.